All right. Good morning, guys. Um, Today, we're going to continue on with using logs and natural logs to help us make data look more linear so that we can use a least squared regression line. But today, we start the process of actually solving with these lines instead of just creating them and using them to make predictions and things like that. All right. So to do that, we have to remember exactly how logs work and how to solve logs. So first off, we need to remember that if it's a regular log, that it's assume that it's base 10, or not just assumed, it is base 10, and that for a natural log, that is natural log is base e, right? So log 7 is the same thing as log base 10 of 7. Those things mean the exact same thing. All right, the way this is going to work for us today when we end up solving it. Some of you guys might remember a process called Smiley. Some of your teachers called it something different. But basically, what we're going to end up with is if we think about like our corona equation, we log the y values but not the x values. So when we plug in on the right hand side, we'll end up getting some number. We'll say, our y-intercept plus our slope times our x value, and we'll end up with some number. So we'll have the log of whatever we're trying to predict. Maybe it's cases had or fees had or whatever we're trying to predict. And then we have to solve this. Okay, so today's a little bit more like a normal math class than normal. So we're going to say 10 to the 0.653, right? Because we know this is base 10. So 10 to the 0.653 equals whatever we were trying to predict, right? And we just type that in our calculator to get the number. In this case, it turns out to be 4.498, right? But solving logs is going to unlock our equations, right? So our calculator will spit out the least squared regression line. We'll know where to add the log or natural log, and then we'll solve it by working backwards. So let's walk through some examples of this. So these are some examples we would have been doing today. A little bit pessimistic because it talks about how a country's income measured in gross domestic product has a lot to do with child mortality rate and really anything health associated. Your gross domestic product is usually correlated pretty well with. So we sketched the scatter plot. It was curved, pretty obvious sign. As gross domestic product went up, child mortality rate went down, but not at a linear association. It was definitely curved. Okay, so least squared regression line, not appropriate. So we chose to straighten the association. There's our proof from the other day, same exact proof that we wrote out in our first video. Okay, so what happens now is, in this case, it turned out to be better to log the y values and the x values. And we chose a natural log here. Remember, either one will work, natural log or regular log. So this was in L1 and L2. And we took that, we hit linreg on our calculator. It spit out the 11.495 and the 0.937. And then we knew that, hey, I logged the y values and I logged the x values. So we add our logs right there. So boom, looks good. Residual plot looks good. The model's appropriate. But now we need to actually solve with this, and that's the difference between today. So we got log here, natural log there. We have natural log there because we did it to the x and y data. The L1 and L2 got logged. If you think about our corona, we ended up with the best model being just logging the y values. Okay, so the question is, predict the child mortality rate for the United States who has an income per person of $41,256. So they are going to give me the income. So that's going to get plugged in right here. And then I'm going to work backwards to solve for the rate. So I plug in natural log of 41,256, which is just some number. I don't know it off the top of my head, but my calculator does. So I do some fancy, type it in my calculator, and this is a number. I subtract the 11.495 over I divide by the negative 0.937, and I eventually end up with some number equals a log, or in this case, a natural log, which is what we said how these problems are going to end. So again, I'm going to take my base, raise it to the power on the other side. So this is where my smiley comes in, or what I call smiley, but e to the 0.9258 is will give me the rate, and we end up with 2.52%, which if I go back and look at my data table, that would fit in about where we would think, right? So even though the calculator spit out these two numbers, which I need, because we know we log the x values and log the y values in this case, we've got both in there, and actually plugging in to solve for the equation isn't just all calculator stuff. It's you having to think just a little bit. Whereas before, it was when there were no logs, it was just straight plug and chug. It was you thinking just a little bit. Okay. So that was a power model where we logged both sides. Now we think about an exponential model. There's our same proof from the other day, and why it works. But we think about an exponential model, and this one also not particularly positive for you guys, but it's talking about mandatory fees for a college, in particular, the University of Arizona. And it's talking about how it's increasing exponential. So what we find here is an exponential model is better. So we didn't natural log the x values, that's just years. We log just the y values. So we end up this time with an equation of natural log of fees, and I got one log over here, but not over here. So, and in this case, we compared them and tried to decide which one was better. And your homework's going to ask you to do that some today is, hey, here's a graph of the exponential model. Here's a graph of the power model. Which one do you prefer? And you're just looking at which one makes it more linear and which one has the better looking residual plot with the most randomness in the y values. So we like the exponential model because it had slightly stronger linear form and no pattern in the residual plot. So because it's an exponential model, boom, there's only one log, or in this case, natural log. Remember, log and natural log, either one will work. All right, so there's only one this time. And they want us to predict the fees for the 2012-2013 year. So now it's telling me the number of years, and it's years since 2000, so we plug in 12. So boom, we end up with natural log fees equals some number, which is how these problems are going to end, with either log something or natural log something. So again, e, take my base to the power on the other side, fees equals e to that, and we get about $1,053 in fees in 2012